Hey folks, my name is Nathan Johnston. Welcome to lecture 5 of vector calculus, which is all about how to parametrize a curve by arc length. Okay, so what that means, what we're going to be looking at in this video is you've got some curve in space and you'd like to parametrize it. In other words, you'd like to find a path that traces out that curve. Okay, we already know how to do that basically. Okay, we know how to find paths that trace out curves, but we're going to be taking that one step farther. How can I find a path that traces out a curve and has the additional property that the parameter just specifies how far the particle has moved along the curve? Okay, and this is a little bit different from how we've been doing things so far. Up until now, we've been thinking of the parameter in the path, the t value. In other words, we've been thinking of that as time. We've been thinking of that as, well, how much time has passed since the particle started moving. Now we're going to flip things a little bit and instead say, okay, I'm not really interested in like the movement. I'm not really interested in it's going fast and slow, then fast and slow. I'm just interested in the geometry of the curve. Okay, so how about instead I parametrize things so that the parameter tells me how far along the curve the particle is, and that particle then, it's just going to move at a constant rate, a constant speed of 1 along the curve. How do we do this? Okay, and maybe before we get into the weeds and show you how that works, how we can actually always do this, let's start off with just an example to remind you of one place where you've seen something like this. Okay, so let's talk about the unit circle excluding the leftmost point, excluding this point -1, 0. We've seen two different parametrizations, or two different paths that trace out this curve, and sort of the simplest of them is this one based on trig, right? Just cos t sine t, where the domain is from pi to 3 pi, excluding the endpoints so that we exclude this leftmost point here. Okay, that's one parametrization, but we've seen a weirder one. Back in our very first lecture video, we saw this path here, which we argued traced out the exact same unit circle, but there's something very different about these two parametrizations, and that is, this bottom parametrization, this g of t, it traces it out in such a way that when the particle moves around that circle, it goes very, very slow over at the left side of the circle, then it goes really quick at the right side, and then it goes very slow at the left side again. Whereas this top parametrization, it's kind of much nicer, right? Okay, instead for this parametrization, the particle is just moving around the circle at a constant speed of 1. Okay, and that's what we like. That's what we're going for here. We want to show that, okay, now if you give me any curve, okay, it's going to have to be sufficiently smooth for all this to work out, but if you give me basically any curve, can you find a parametrization for it? Can you find a path that has the property that it traces out that curve and its speed as constant at 1? In other words, the parameter, I can think of it as just specifying how far along the curve the particle has moved at that point. And it turns out that basically, yeah, you can always do this. You can always, if you're given some curve that's traced out by a continuously differentiable path f, then yeah, you can find a new path, f tilde is what we're going to call it, that traces out the exact same curve. It has the additional property that the parameter in this new path, it just tells us how far the particle has moved along the curve. Okay, so in other words, like f tilde at 0, that's just going to give us one of the endpoints of the curve. And then if I plug in L equals 1, for example, that's going to be what I would get if I walked a distance of 1 unit along the path. And then L is 2, that's 2 units along the curve, and so on. Okay, or another way of thinking about this is this new path f tilde, it has the property that its speed is a constant function. Its speed is 1 everywhere. So the particle, it's not going slower than fast and slower than fast. It's sort of a normalized or a regularized version of this original path f. Okay, so how do we do this though? How do we actually come up with this new parameterization or this new path f tilde? Okay, and to start, like really the goal here is to find a connection between these two parameters L and T. And to start, we're going to remember that, well, we already have that connection, right? Remember that the relationship between the distance that a particle has traveled and the time that it's been traveling for is given by this function here, right? Last class, we talked about how, how do you compute the length of a curve? Okay, in other words, like if I want to compute, okay, this particle, it's been traveling from the left endpoint t equals a up to some new t value. How far is that? Well, you just integrate the speed from t equals a up to your new t value. Okay, and this tau in this formula here, like really, like this is my t in my original length of the curve formula. It's just unfortunately now I'm using t up here as one of the endpoints of the integral, and I can't use it in here, right? So I just need a dummy variable, but like really this is just the t value as well. Okay. Now, this is sort of like the key insight that gets us most of the way there, but we have some technical details that we've got to deal with. The first detail is that, okay, if I have a t value in mind, this gives me a way of computing L from it. That's not really what I need though, okay? I need to flip this around. I want, if I have an L value, then I can compute a T value from it, because if I had such a function, if I had T as a function of L instead, then what I could do to come up with a formula for my F tilde, for the path that I want, what I could do is I could just take my original parametrization, or my original path F, and everywhere that I see t in this formula, just replace that t by my new formula for t in terms of L. Okay, and then that would trace out the exact same curve, but now the parameter would be L everywhere instead of the original parameter t. Okay, so how do I do this? How do I actually find, t in terms of L instead of L in terms of t? And like what I could do is I could just compute this function explicitly and then invert it. You learned how to invert functions in a previous course, right? This is just a function of one variable. There's sort of nothing new here. Okay, but maybe I should talk about how we know that actually we can always invert it. How do we know that L of t is an invertible function? And there's one slight technicality that we've got to deal with here, and that is, well, it's not actually always an invertible function unless we make a slight extra restriction, and that extra restriction is that we only consider paths that have non-zero speed everywhere. We've got to assume that the velocity vector of our path is always non-zero. Otherwise, while the particle is moving along the path, it comes to a it comes to a stop at some particular position, and then at that position, we can't be sure that the function's invertible, right? Because we're asking the question, you know, if I tell you how far along the curve the particle has traveled, can you tell me what the time is? And if it comes to a stop at a particular position, the answer is no, because there are multiple different times that might give you that same L value. Okay, because the particle's just chilling at that L value doing nothing. Okay, so we've got to assume that the particle is just always moving. It never comes to a stop, so its velocity is non-zero. That's going to give us invertibility of this L function. Okay, and if that's true, okay, great. How do I know that the function L is invertible? Well, the first thing that I'm going to notice is that this L function, as long as the speed is non-zero, it's actually a strictly increasing function. And the reason for that is if I plot the integrand, if I plot this thing here, this length of the velocity vector, okay, well, I'm assuming that it's always non-zero. Okay, so in other words, if I plot it, it does not come down to the x-axis. Okay, it's always strictly above the x, or I guess I'm calling it tau here. It's above the tau axis. Okay, so then this L of t, well, remember, like L of t, it's a definite integral. I can think of that as just the area under the curve from the left endpoint A over to the right endpoint t. And L of t, it's just this yellow shaded area here. And what happens as I increase t? Well, this area is going to increase. Every time I move t over to the right, I accumulate strictly more area. So L of t is going to go up. Okay, so this function L of t, it's an increasing function. As you plug in larger values of t, you get larger values of L. And that's enough to tell me that the function L is invertible, actually. Okay, the reason for that, now if I plot L itself, okay, so before I was plotting like the speed and then L was the area under the curve. Now I'm plotting L itself. So like this area in the plot up above is the y value in this plot down here. If I plot that, well, I just argued that L of t is an increasing function. It's always going up. And if you've ever got a function like that, like what you can argue is, okay, if I want to know like what t value results in a particular output, like this particular L1, well, there's only one t value that makes that happen. There's never going to be a second one because there would have to be, a second point where it crosses the graph, but the graph would have to come down for that to happen, and it doesn't. It goes up and up and up. So for each output L value, there's a unique input t value that gives you that output L value, okay? And that's exactly what invertibility is, okay, right? If you're given the output, can you determine what the input was uniquely? That's invertibility, and that's what we wanted. Okay, so yeah, this function is always invertible as long as the speed's always non-zero. So we can do this reparametrization by arc length. So let's throw all this together into a theorem. Like what did we just sort of argue is true here? And then we'll do a couple numerical examples. Okay, so here's the setup. Suppose that you want to parametrize some curve by arc length. The first thing you've got to do is just find some parametrization, find some path. It's got to be C1. It's got to have continuous first derivatives. Find some path that traces out that curve, okay? And furthermore, you've got to choose your path so that its speed is never zero. Okay, then how do you reparametrize it by arc length now? How do you find a better parametrization of it? Okay, well, what you do, first off, you define that L function that we were talking about, the length so far function, the function that measures the length of the curve from an arbitrary starting point. That's what T0 is. It's just any point in the interval that I'm sort of thinking of as the starting point, this point where I start measuring length, and then up to the right endpoint, which is my variable. The right endpoint is my t, and this measures the length from t0 up to t. So I define that function. Then what I do is I note that, hey, that function's invertible. Yay. You invert it so that you get a function of the form t of L, right? T in terms of L now. Okay, and then you define a new path, f tilde, via this formula. What you do is you just take your original path, f, and you plug t of L into it, and now you've only got L's everywhere, and that's your new parametrization that you wanted. That's what we're calling f tilde. Okay, and when you do this, it does exactly what you want. It's going to give you a new path that traces out the same curve, and furthermore, its speed is going to be constant at 1. It's always moving at a rate of 1 unit of distance per unit of time. Okay, so let's actually try to do this. Let's play around with some examples, okay? Let's play around with the helix. We've seen the helix a couple times before in this course already. Remember, the helix is just given by a cos t, a sine t, bt, where a and b, those are just fixed real numbers. A is the radius of the helix, and b is sort of how stretchy it is in the z direction. We're going to reparametrize this by arc length now, starting at t0 equals 0. In other words, that's sort of where we're measuring length or distance from, okay? While the particle's there, we say it's traversed 0 distance, and that as it moves past that point, we start adding up positive lengths. Okay, so how do we do this? Well, first off, write down that function L of t that we need to do this parametrization by arc length, right? It's just the distance traveled so far function. It's the definite integral of the speed function. So we need this velocity vector. We need f prime. Just take the derivative of each entry. And when we do that, right, cos becomes negative sine, sine becomes cos, and bt just becomes b. And then we compute the length of that, right? And speed is the length of the velocity vector. So you just take these entries, square them, add them up, okay? And we've still got this integral sign outside of everything. And now we'd love to integrate this thing, but let's do a little bit of simplification first. Remember that sine squared plus cos squared equals 1. So that's going to simplify down really nicely. Now I've got the integral of this junk here with respect to tau. Okay, and that's important because this stuff in here doesn't have any taus anymore, right? They all went away when I used my trig identity. Okay, so this is a constant as far as tau is concerned. When I integrate it, I just get a tau, and then I plug in my endpoints. I plug in a t and a minus 0. I'm just going to get this constant times the width of the interval, which is t itself. Okay, so that's my L of t function. And then to go on from here and to actually, do the parameterization by arc length, what I've got to do is I've got to invert this. I've got to get t in terms of L. So I say, okay, well, I've got L equals this junk times t. Just rearrange that so it's t equals what in terms of L. In other words, in this particular case, just divide both sides by this root of a squared plus b squared, and you're going to get t in terms of L looks like this. T is 1 divided by that square root of a squared plus b squared times L. Okay. And then last but not least, all you do is you go back to your original function and you say, okay, f of t equals this junk, but wait, t equals that junk. Just sub this t in for all the t's up here and you're done. Okay, what you're going to get is, f tilde of L, my new path, my new parametrization, it's f of t of L. Just replace all the t's in f of t by this new formula here, okay? And then what that looks like is, well, a cos t, well, that becomes a cos times that crap, which just has L's in it, okay? And then a sine t, well, replace all the t's by that formula. And same thing on the right, b times t, no, that's b times L over root a squared plus b squared, okay? So that right there, that's my parametrization by arc length. And I mean, in my original helix, like kind of implicit in this calculation here is that any of these helixes, okay, any of these original parametrizations, the speed of the particle is already constant, okay? Like it doesn't depend on where the particle is on the helix. It's going around at a constant rate, but it does depend on the radius of the helix and how stretchy it is in the z direction, okay? And what this reparametrization does is it removes that dependence on A and B, the radius and the stretchiness, so that now the particle is just always moving at a rate of 1 around, regardless of how big and stretchy the helix is. Okay, let's do another example. Okay, so this time we're going to do this for a spiral. Okay, so suppose that you've got this path from R to R2 defined in this way. And it turns out that, yeah, this traces out a spiral in R2. Kind of what's happening here is the cos t sine t is making the particle spin around the origin. And then this e to the at is making it move out further and further away from the origin as time goes on, because it's blowing up the magnitude of this path as time gets bigger and bigger and bigger. Okay, so here's the question: how can we reparametrize this in terms of arc length? Okay, and well, let's just do what we always do. Okay, plug things into the formula. Okay, so to start, we're going to need the velocity vector, then the speed vector. Sorry, velocity vector, then speed, which is the magnitude of that velocity vector, then integrate, then invert, and then plug back into the original path, and we'll get what we want. All right, so one step at a time. Velocity vector, just take the derivative of each entry, right? And I mean, both of these things that are being multiplied together, they all involve t, so we need a little bit of product rule here, right? Derivative of e to the at is a e to the at times cos t, no derivative, and then minus e to the at, no derivative, cos derivative is sine. Okay, so I'm just doing product rule on that first entry to get this thing here, and product rule on the second entry similarly gives me that thing there. Okay, next up, magnitude of that vector. Okay, compute the length of it. In other words, take the first entry, square it. Take the second entry, square it. Add them up, then square root the whole thing. Okay, and what's going to happen when I do that is I get, well, okay, some ugly junk. Okay, so here's the speed of that path. And I'm going to simplify that down a little bit. And the way I'm going to do that is, okay, let's expand out the squared brackets. Okay, and when I do that, I get a squared cos squared. I get a sine squared. And I'm also going to get a cross term, which is negative 2 times a cos t sine t. But when I square this one out, I'm going to get the exact same cross term, but positive. I'm going to get plus 2 times a sine t cos t. That's the same thing. The two cross terms cancel each other out, which is why they're not written down here. Okay, and then the 4 terms here, it's just the squares of these 4 terms. Okay, and now something really nice happens. I can use everyone's favorite trig identity, sine squared plus cos squared equals 1 again. Okay, and if I do that, like I've got an a squared cos squared, an a squared sine squared, oh, that just becomes a squared. And then I've got a sine squared plus a cos squared, that gives me an extra 1, all still underneath the square root sign. Okay, so that's my formula, about as simplified as possible for the speed of this path. Okay, next up, I integrate it to get my L function, my length so far function. So I'm just going to take this formula here, plug it into the integral. Okay, and now it's going to be an integral from negative infinity to t. Okay, and this is a little bit weird here. Okay, I said, okay, yeah, t0 is negative infinity. And this is admittedly something I glossed over. This is okay as long as this integral that you get here, I mean, this is an improper integral now, right? Because like this left point being at negative infinity, strictly speaking, that's defined in terms of a limit. Like that's the limit as this left endpoint goes to negative infinity. As long as that limit or this integral converges, then this is all a fine thing to do. Okay, and it turns out, yeah, this integral is going to converge, so it's all okay. Anyway, so let's compute this integral. The only thing that has a tau anywhere in here is this e to the a tau. Okay, and when we integrate that, I get 1 over a e to the a tau, and I plug in my endpoints. When I plug in the right endpoint t, it's just plugging in t, and nothing like that. You can't simplify that any further. This constant root a squared plus 1 just becomes here. And the negative infinity, sort of what happened to that is, remember, like you're taking the right endpoint, plugging it in, and then subtracting what you get when you plug in the left endpoint. And this left endpoint, when I plug it into this after integrating it, I get e to the negative infinity, like in the limit to make all this precise, and that's going to be 0. Like really what's going on here is I've got a minus 0 here, but I don't bother writing that. Okay, so anyway, so this is my length so far function. Great. Now flip it around. Get t in terms of L instead. Invert this function. Okay, so first thing I'm going to do is move the constant over to the other side. In other words, multiply both sides by a and divide both sides by the square root of a squared plus 1, and you're going to get, that new constant times L equals just this e to the at term. So I've just moved this constant over to the left. Okay, and now again, I want t equals something. So I've just got to unwrap this piece here. I'm going to take the natural logarithm or ln of both sides and then divide both sides by a. And when I do that, I get t equals this junk over here. And it's kind of ugly, but it just is what it is. Okay, even though like sort of the formula for it is maybe a little bit uglier than I would like, sort of like the result of it is going to be nice. Okay, sort of geometrically, this is going to be a nicer parametrization than the one that I started with. Okay, anyway, now all I do is I've got t in terms of L. I'm going to go back up to my original formula for the path, replace all the t's that I see by this formula that's highlighted in yellow down here. And when I do that, and after simplifying just a tiny little bit, like I'm going to be able to simplify, because for example, e to the at, if I apply that to this, the divided by a cancels out the a up there, and then the e to something gets canceled out by the ln. Okay, so this chunk here, this al over square root of chunk, that's the e to the at. It's just been simplified a little bit. But yeah, that's all I'm doing. I'm replacing every single t in this formula by this formula. And now everything is in terms of L, and that's my parametrization by arc length. The way to think about this geometrically is in the original parametrization, in the original path F that we had, the particle was moving very, very slow near the origin. When it's doing sort of those inner loops of the spiral, it's going very, very slow. But then when it gets out to the big loops around the edge of the spiral, now it's going very, very fast because those loops are big, right? In the original parametrization, every time t went up by 2 pi, it's looped around the origin one more time. Okay, and if those loops are small near the center of the spiral, well, then it didn't go very far. But if the loops are big, sort of further out from the center of the spiral, those loops are huge. Okay, so the particles started off moving very slow and then moved very, very fast. Okay, and then this new parametrization, the one in terms of L, this F tilde, it doesn't do that. Instead, it really moves a constant distance per unit of time. So if it's near the center, near the small loops of the spiral, it's doing tons of those loops very, very quickly, but it's not actually very quickly. It's just sort of lots of spins around because the spins around are so small. And then when it gets to the big loops around the edges, it looks like it's moving slower, but it's not. It's still like moving 1 unit of distance per time. It's sort of not spinning as quickly anymore because sort of the loops that it's spinning around are bigger and therefore take longer for it to get around. All right. Maybe before we close the video, I should note that doing this in practice is often extraordinarily difficult, okay? And where that comes from is that, like, this function here, L of t, well, computing this integral is often very, very difficult. And then furthermore, you've got to invert it, and that might be very, very difficult or even impossible. You might not be able to do this in closed form, okay? But even in spite of that, this is a very useful technique to know is possible in theory, okay? The fact that this reparametrization by arc length exists, that's going to be an extraordinarily useful theoretical technique as we go on to try to prove theorems about curves later on in the course. And even starting, in the next lecture or two, we're going to be making use of this theoretical fact that a reparametrization by arc length at least exists, even if it's really hard to compute, in practice. All right, so we'll take care of that over the upcoming lectures. For now, I'll just leave it there, and I'll say thanks for watching, everyone. Have a good one. See you next time.